This is the Unit 4 review for the Unit 4 exam in Math 1111 in spring 2020. I did provide you an answer key, but in this video I'm going to walk through and provide the additional explanation of working the problems. So it says for question 1 to use the parent graphs transformations to ultimately graph, although I'm not going to ask you to graph it on the test. You have to identify the parent, the vertical translation, horizontal translation, whether there's a reflection on X and a reflection on Y. Remember, with the exponential and logarithmic, I indicated there would not be a vertical shrink or stretch. And so my parent here is given to me actually as 4 to the x, which is an exponential function. I recognize it as an exponential function because it has the variable in the exponent. The function that I'm asked to deal with is f of x equals 4 raised to the x plus 1 power minus 2. And so I need to identify A, B, C, and D. Okay, so remember, I'm going to make my pen a little bit smaller here, so hopefully it'll be a little bit easier. A is the 4. B is the number in front of the x. C is the constant in the exponent, and D is tagged at the end. So the vertical translation, if you'll recall from Unit 2, is determined by D. D in this case is minus 2, which tells me I need to go down 2 units. The horizontal translation is actually determined by C, but we want to be careful so that we don't make an error. We take the expression in the exponent, the x plus 1, set it to 0, and we solve for x so that I can see that x is actually -1 or -1, which means we're going to go left 1 unit. The reflection on x is determined by the sign of A. A is positive, so there is no reflection on x. And then finally, you have the reflection on y, which is determined by the sign of B. Again, in this scenario, B is positive, so there is no reflection on the y-axis. And again, I mentioned to you in respect to exponential and logarithmics, there will be no vertical stretch or shrink. There could be, but we didn't get that detailed about it. All right, the next one is a logarithmic function, and we're asked to do the same thing. Here again, it identifies my parent for me as the natural log of x. And again, I hope you recognize that as a logarithmic function. The function that we need to deal with is the opposite of the natural log of x minus 1 plus 2. Again, you want to identify your A, B, and C. Remember, A is the number out front. B is inside with the parentheses with the x. C is the constant inside, and then D is tagged at the end. Again, our vertical translation is determined by D, which in this problem is positive 2, so we're going to go up 2 units. the horizontal translation is determined by C. Again, we want to avoid making a sign error, so we take the expression in the parentheses, set it to 0, and solve, and we get x equals positive 1. So we can see that it's positive, so we're going to go right 1 unit. The reflection on x is determined by the sign of A. A here is an understood -1. Since it's negative, there is a reflection on x. And then finally, we have the reflection on y, which is determined by the sign of B. B is positive, so again, there's no reflection on y. Again, you get to use your notes, so I would take good notes. The original discussion for transformations of functions occurred in Unit 2. All right, then the next few questions, and it's not 7 through 10, it's 3 through something, but the instructions say, use the properties of logarithms to expand each logarithmic expression as much as possible. Where possible, evaluate logarithmic expressions without using a calculator. So we don't want to have decimals. If we can simplify it to a whole number, then we'll do that. And I'm going to indicate which property I'm using, okay, from the PowerPoint. You do not have to indicate which one you're using on the test. So the first one I see is log base 3 of 10z. 10z written side by side implies multiplication. And I remember from property 1, I'll put P1, that multiplication is rewritten as addition. So this would become log base 3 of 10 plus log base 3 of z. Now, I want to think about it. 3 to some number would be 10. I can't do that in my head. So that one is as simple as it would get. The second one, number 4, we have log base 5 of 5 over x. This is division. Your argument is division. Property 2 tells us that division is rewritten as subtraction. So this becomes log base 5 of 5 minus log base 5 of x. Again, be careful because remember you want to simplify it all the way. Log base 5 of 5 to the first. Remember that a logarithm and an exponential of the same base are inverses. They cancel one another off. So this becomes 1 minus log base 5 of x. This would be the appropriate answer because you're asked to simplify it as much as possible. And I can do log base 5 of 5 in my head. Number 5, we have the natural log of x times y to the 4th, all divided by z to the 5th. So initially, when I'm looking at my argument, I see division. And I know from property number 2 that division is rewritten as subtraction. So I would have the natural log of xy to the fourth minus the natural log of z to the fifth. Not finished, because I notice in this first term, natural log of x times y to the fourth, okay, that is multiplication, and multiplication is rewritten as addition. That's property 1. So I would expand that out a little bit further. The natural log of x plus the natural log of y to the fourth minus the natural log of z to the fifth. It tags along. It doesn't go away. The last thing that I notice is that two of the terms, the second term and the third term, have an exponent. That again is not allowed. And so property 3 tells us how to deal with that. That basically this is the power to the power. So we multiply it. So we would end up with the natural log of x plus 4 times the natural log of y minus 5 natural log of z. Again, this is the most appropriate answer because you have it in the simplified form. And then number 6. Number 6 is the natural log, or excuse me, the common log or log of x to the fourth times the square root of x squared minus 3, all divided by the quantity x minus 3 to the fifth. Again, initially I notice in my argument that I have division. And I know from property number 2 that division is rewritten as subtraction. So I'm going to have the natural log of x to the fourth times the square root of x squared minus 3 minus the natural log of the quantity x minus 3 to the fifth. Not finished, because I noticed that this first term has multiplication. Multiplication is rewritten as addition based on property 1. So I would have the log of x to the fourth plus the log of the square root of x squared minus 3 minus the log of x minus 3 to the fifth. I notice that in this second term I have this square root symbol, and I remember that a square root can be written as a fractional exponent. So I'm going to rewrite the square root of x squared minus 3 as the quantity x squared minus 3 to the 1/2. Okay, so I've rewritten that in terms of a fractional exponent. You should always do that with radicals in relationship to logs, is transform them into fractional exponents. Then I notice that all 3 terms have an exponent. And so that's property number 3. So I would have 4 times the log of x plus 1/2 times the log of x squared minus 3 minus 5 times the log of x minus 3. Okay, guys, you can't do anything else. Be careful, because sometimes people or students want to try to do something with this x squared minus 3 or the x minus 3. Remember in math class that when they're connected by a plus or minus sign, they're married, and you can't just separate them because you want to. Also, none of the properties talk about doing anything if you have subtraction, which is the operation in both of those pieces. So this would be your most appropriate answer, is this one here in green, 4 log x plus 1/2 log of x squared minus 3 minus 5 times the log of x minus 3. Okay, then we get down to basically this would be change of base. If you don't catch the instructions, it says use common logs or natural logs and a calculator to evaluate it and round your answer to 4 decimal places. So this is where you would use or apply the change of base formula or the change of base property. Remember, the formula is log base b of m equals log base a of m divided by log base a of b. And so the question that I'm given is log base 7 of 4. So I have my b is 7, my argument is m, which is 4. So I'm going to convert that to common log. So I would do log of m, which is 4, divided by log of 7. Now again, let me caution you, because when you put this in your calculator, you need to make sure that you close the parentheses around your argument. Okay, I don't have my calculator pulled up, so it's going to take me just a minute to get it pulled up, so be patient. And then you're going to type it in. Some of you may have a calculator that has the command that'll do it all for you. I think it's just as easy to use the formula. Okay, so I would have the log of 4 divided by the log of 7. The log of 4, make sure to close the parentheses, divided by the log of 7. Make sure to close the parentheses and hit enter. And when it wants 4 decimal places. So I have 7, 1, 2, 4. That's the 4th place. Next to it is a 1. So we're not going to round up. So it's 7, 1, 2, 4. So the answer here would be equals 0.712, rounded to 4 places. Then the last, well, there's really 2 sections left. You have solving equations, whether they're exponential or logarithmic, and also some application problems. So number 8, we begin to solve equations, and my equation is 5 raised to the 3x minus 1 power equals 125. It is an exponential function or equation because I have variables in my exponent. Okay, so this is an exponential equation. Oops, sorry about that. It kind of jumped on me there. Okay, so this is an exponential. And to solve an exponential, we use a logarithm of the same base. So I notice that my exponential has a base of 5. So I would do log base 5 of both sides. So we're going to do log base 5 of 5 to the 3x minus 1 equals log base 5 of 125. The benefit of that, remember, is that a logarithm and an exponential of the same base cancel one another off. So I have 3x minus 1, and that equals log base 5 of 125. I think I'm familiar enough with log base 5 of 125, so I'm going to go out and see if that gives me a nice neat number or if I'm going to have to deal with decimals. But to do that, I need to take this value, log base 5 of 125, and do change of base. So I would have the log of 125 divided by the log of 5. I'm going out to my calculator. Let's see. Log of 125, close the parentheses, divide by log of 5, close parentheses, enter. And it's 3. Okay, so I get a nice neat number. So I can go ahead and replace that. So this becomes 3x minus 1 equals 3. So I kind of get a nice equation now. That's good old basic algebra. So I'm going to solve for x. I need to add 1 to either side. So I have 3x equals 4. And then I'm going to divide both sides by 3. So ultimately my answer is x equals 4/3. Okay. There's a lot of little steps in there. All right, number 9 is 9e to the x equals 108. Again, I notice that this is an exponential because the variable is in the exponent, but my exponent piece, my e to the x, is not isolated by itself as it was in the first problem there. So the first thing I'm going to do is get it by itself, and to do that, I have to divide both sides by 9. So I have e to the x equals 12. 108 divided by 9 is 12. Then I have a reasonably simple exponential equation. We're going to solve that doing log by taking the log of both sides. So we're going to take the natural log of both sides. I'm using natural log because my exponential has a base of e. So we're going to have the natural log of e to the x equals the natural log of 12. Again, the benefit of that is that the natural log base e and the exponential base e will divide out, so that we have x equals the natural log of 12, which would be the exact answer if we needed it. I can use my calculator to get an approximation. On my calculator, I would type ln 12, and if we round to say 3 places, we'd have 2.485. Okay, so x will be approximately 2.485. That's our estimate that we get from the calculator. All right, number 10, I have 4 times e raised to the 7x equals 10,273. Again, hopefully you recognize it as an exponential because the exponent contains the variable, but it is not isolated. So I need to get the exponential portion isolated by dividing both sides by 4. So I have e to the 7x equals 10,273 divided by 4. Now, I don't think that divides evenly, but let me see if I can go out and simplify that a little bit. 10,273 divided by 4. 250, 2568.25. Since it's a decimal that's terminating, I could use that. So 2568.25. So I have e to the 7x equals 2568.25. Make sure I got that right. Yep. Okay. Then I have base e. To undo base e, we use the natural log. So I'm going to take the natural log of both sides. So I have the natural log of e to the 7x equals the natural log of 2,568 and 25/100ths. Again, the whole point of taking the natural log is because natural log base e and exponential base e will divide out, and I have 7x left equals the natural log of 2,568.25. And I'm ultimately trying to solve for x. So I would divide both sides by 7 so that x equals the natural log of 2,568.25 all divided by 7. And again, that would be your exact answer. I can put it into the calculator. Natural log of 2,568.25, close the parentheses, and divide by 7. And I get 1.122 if we round to 3 places, excuse me. 1.122 if we round to 3 places. Okay, then we switch gears, and in the next few problems, we look at logarithms. And again, we have to remember that logarithms and exponentials are inverses of each other. So number 11, we have log base 5 of x minus 7 equals 2. So I notice it's a logarithmic equation with a base of 5. So I'm going to use an exponential base 5. So I would have 5 and raise each side as my exponent. So I'd have log 5 raised to the log base 5 of x minus 7 equals 5 squared. Again, our benefit there is that an exponential base 5 and a log base 5 will divide out, so that I have x minus 7 equals 5 squared. And I can do that in my head. That's 25. And then I have just a good old everyday equation. I'm going to add 7 to either side. So x is 32. And again, I want to think about what happens when I plug that back in. Okay, my argument is not negative, it is positive, so I'm okay. Remember, your argument has to be positive. Number 12, I have 4 times the natural log of 7x equals 8. Again, I notice I have a log in there, so it's a logarithmic equation, but it's not isolated. So the first thing I need to do is isolate it. So I'm going to divide both sides by 4, which gives me the natural log of 7x equal to 2. And then I need to use my inverse property. So I need to use base e. So I'm going to raise both sides to e. So I have the natural log, e to the natural log of 7x equals e squared. Again, the benefit of that is that the logarithm base e and the exponential base e divide out. So I have 7x equals e squared. I am trying to solve for x ultimately. So I would divide by 7 on both sides. So that I have x equals e squared divided by 7. And again, that would give me the exact value. I can get a decimal approximation on my calculator. I would do e, which is the second ln squared, get out of the exponent, divide it by 7. And I get 1.056 if I round it. 1.056. So this is approximately 1.056. That would be my estimate. Okay, number 13. Log base 3 of x squared minus 2x equals 1. And again, I recognize it as a logarithmic equation because it has log in it. It's a base 3, so I need to use an exponential of base 3 to help me solve it. So I'm going to have 3 raised to the log base 3 of x squared minus 2x equals 3 to the first. Again, the benefit there is that an exponential base 3 and a logarithm base 3 cancel one another off. So I have x squared minus 2x equals 3 to the first, which is just going to be plain old 3. And you have to recognize that that particular equation is a quadratic. And we solve a quadratic either by factoring or using the quadratic formula, but the equation has to be set equal to 0. Whether you're going to factor or use the quadratic formula, you have to have the equation set equal to 0. So I end up with x squared minus 2x minus 3. Again, I know that most of you prefer to use the quadratic formula, so that's what I'll do. A is 1, B is -2, and C is -3. So we would have x equals the opposite of -2 plus or minus the square root of -2 squared minus 4 times A times the -3. I had to squeeze it in there. Divided by 2 times A. So that gives me +2 plus or minus the square root of 4. -4 times 1 is -4 times -3 is +12 over 2. So I have 2 plus or minus the square root of 16 all over 2. 16 is a perfect square. It's 4. So I end up with 2 plus or minus 4 over 2. So we would have 2 plus 4 over 2, which is 6 over 2, or 3. Or we would have 2 minus 4 over 2, negative 2 over 2, which is negative 1. But guys, remember, the argument has to be positive. So if I go back and I check these two numbers, it should be obvious when I plug in a positive number that I'm going to get positive, but we can double check. 3 squared is 9. So 3 squared minus 2 times 3, that gives me 9 minus 6, which is 3. I'm good there. If I plug in negative 1, I would have negative 1 squared minus 2 times negative 1. So I have 1 whole plus 2, which again is 3. In this case, the negative 1 is actually permissible. Okay, so you actually have two answers to this problem. They are positive 3 and negative 1. But guys, you got to go back and check it and make sure the argument is not negative. Okay, we got 3 questions to go, and they're the application problems. Number 14 says Emily borrows $15,000 at an annual interest rate of 6.75%, compounded monthly. Find the balance after 7 years. Okay, so first thing that jumps out at me is that it's compounded monthly, which tells me to use the formula A equals P times 1 plus R divided by N to the NT. I'm told that she originally borrows $15,000, that the rate of interest is 6.75%. I need to change that to a decimal. 6.75 divided by 100 is 0.0675. And we want to know how much money she would have after 7 years. Whoops, wrong number there, sorry. After 7 years, when it's compounded monthly. Okay, so monthly is my compounding, and there are 12 months in a year, and we want to know what happens after 7 years. Okay, so we're going to plug and chug. We're going to plug and chug into the formula. So I would have A equals 15,000 times 1 plus 0.0675 divided by 12 raised to the 12 times 7 power. Okay, so I'm going to do 15,000 times 1 plus 0.0675 divided by 12. I'm going to go ahead and do 12 times 7, which is 84. Guys, I'm not going to do those calculations by hand. I'm going to go out to my calculator and walk it through. Okay, so I'm going to clear this out. We start with the piece that's in the parentheses. We start with the division. So we take 0.0675 and divide it by 12. We add 1. We raise it to the 84th power, and then we multiply that times 15,000. So at the end of 7 years, Emily would have $24,028 and 15 cents if you round it to the nearest cent. It is money, so that would be standard, rounding to the nearest cent. Okay, so ultimately my answer here is she would have $24,028.15. All right, this problem says, on the day of Thad's birth, a deposit of $25,000 is made in a trust fund that pays 8.75% interest, compounded continuously. Determine the balance in the account on Thad's 25th birthday. Okay, so what jumps out at me initially in this problem is it says continuously, because that determines my formula. So my formula here, because it's continuously, is A equals P times E to the RT. Okay, it tells us in the story that $25,000 was deposited into a trust fund on the day that he was born. The rate of interest is 8.75%, which we do convert to a decimal. So 8.75 divided by 100 is 0.0875. We want to know how much money would be in the account on his 25th birthday, and it even says let T equal 25. So here again, don't overthink it, guys. It is a straight plug and chug. So I'm going to have 25,000 times E raised to the 0.0875 times 25. And again, I'm going to use my calculator. I'm not going to do those calculations by hand. Okay, so let me clear it off again so you'll only have those numbers on the screen. So we type it in just like we see it. 25,000 times E, second ln, the E pops up, 0.0875 times the 25 years. All of that's in the exponent. Arrow out, equals. He would have $222,822.57. Okay, guys, you got to utilize the calculator. So he ends up with $222,822.57. The last one is a logarithmic problem, okay, where they give you the formula. It says the antler spread, A, in inches, and shoulder height in inches of an adult American elk, male American elk, are related by the model. H equals 116 times the log of A plus 40 minus 176. And it wants us to approximate the shoulder height of a male American elk with an antler spread A equals 45. So they give you the formula, they give you the value, in this case, of A. So I would have H equals 116 log of 45 plus 40 minus 176. Now I'm going to do one piece in my head. 116 log 45 plus 40 I can do in my head. That's 85. So I have log of 85 minus 176. Calculator, calculator, calculator. So we would type 116 times the log of 85, close the parentheses, minus, I forgot the formula, minus 176, because that's what the formula says, 176. Enter. So it would be 47.813 inches, again, typically rounding to 3 places. So 47 equals 47.813 inches. Okay, that concludes the Unit 4 review. Okay, the Unit 4 test will open on Saturday, May 2nd, and will close on Tuesday, May 5th at 11:30 p.m.